So okay, so today's class, basically I will be talking about the development of control theory using state space model. Before going into that, we have developed the control theory. We have learned the development of control theory using the transform domain model, specifically the transfer function model. As you have seen that the transfer function models are basically input-output models. That means we define what are the control objective. Based on that, we measure the variable, we get the output, and we select the manipulated variable, which is considered as input. So it's basically an input-output model where in this model, we do not have any information of the internal states of the system. For example, if you take one example, like if you want to control the 3-tank system. So in the 3 tanks which are connected in series, if I control the level of the 3rd tank by manipulating the inlet flow rate to the 1st tank, then in that case, I have the information of the 3rd tank only. The information in this case is the level of the 3rd tank. And based on that information of the level of the 3rd tank, I design the controller so that the controller can manipulate the control valve in a specified manner. But in this process, we do not have any information of the level of the 1st tank as well as the 2nd tank. Most of the cases, what will happen is if the tank areas and tank sizes are different, specifically, let's say if the tank size of the middle tank or the 2nd tank is completely different from the other 2 tanks, which is, let's say, the smaller size and the area is small, then what will happen is you can control the 3rd tank level, but at the same time, the level of the 2nd tank may not be controlled, which means that the level, the liquid may overflow from the 2nd tank. So the level of the 2nd tank you cannot control. So in this in this design of controller using input-output model, we basically control the output variables without any control over the states of the system, right? So to overcome this, there is another way of designing the control system, which takes the information of the states also while designing the controller. So this is basically called the controller designing using state space model. So before beginning with this, let me share the slides. Okay, so the session got disconnected. I am again sharing this. Okay, can you see these slides? One of you, please.
Yes, sir.
Yes, sir.
Hello.
Yes, sir.
Okay. So the dynamic behavior of any system can be mathematically represented by state space model. So it is of two types. One is the nonlinear state space model. So I told you that general form of nonlinear state space model is x dot is equal to function of t x u. So this is the general form. This is not a control affine form. The control affine form of model is when you separate out the states and the inputs. So this is basically a control affine form of the nonlinear state space model, where the state equation is given by x dot is equal to fx plus gx into u. Here x is the state variables, u is the input variables, and the output map equation, which is y is equal to hxu. Y is basically the output variables. So the nonlinear state space model contains two equations, two sets of equations. The first set of equation is the state equations or states equation, and the second set of equation is the output map or output equations. Okay, so this is a basically form of the which is control affine. Here basically x is a vector x1, x2, x3, xn if it is a n number of states variable involved. So x dot is the dx by dt. So dx1 by dt, dx2 by dt to dxn by dt. And u is the input variable. So you can have a m number of inputs involved over here. And fx and gx are basically the functions which are connected to function matrices or function vectors which are connected with the states and the input. And hx is the output map function which basically converts from the states and input to the output, or it gives a relationship between the states and input to the output. The second set of representation of state space model is the linear state space model. Here basically y can be y to phi number of our output can be there. So then in case of linear state space model, we can write this equation as a x dot is equal to ax plus bu and y is equal to cx plus du. So in case of a linear state space model, we can write the state equation as x dot is equal to ax plus bu. Here x I am representing as a capital X. All variables over here x, u, and y are capital form because these are basically in deviation form. So the capital X, capital U, and capital Y, all three terms are in deviation forms. So where X, U, and Y are the state variable vector, input vector, and output vector in deviation form. And similarly, if the n number of state variables are there, then you will have x1 to xn, m number of u, and p number of output variables are there. So here basically the A and B matrices are the properties of the system and are normally determined by the system structure and elements. A is basically called the state transition matrix. B is called the input matrix or control matrix. C is basically called the output map matrix, and D is called fit through matrix or fit through vector. So this way, basically A, B, C, and D are defined. Now, how to develop a state space model? How to develop a state space model, whether in a nonlinear form or a linear form? So let us see how we can develop a state space model. The development of the state space model. So the first step is you develop a dynamic model from the first principles. So from the first principles, we can develop a dynamic model which is x dot is equal to fx u, and then once you have a dynamic model, then you define the control objective. Once you define the control objectives, then you have y should be a function of h and xc. Okay, so based on the control objective and from the first principle itself, also you define the function h. So you know the function f, you know the function h, which are basically functions of the state variables and input, and in this case the function of state variables of input, which is an algebraic function, is a differential equations. Once you have that, then you rearrange this equation 1 and 2 to get a control affine nonlinear state space form. So you arrange this one in a form of control affine form, which is x dot is equal to fx plus gx into u and y is equal to hxu. So you'll get a nonlinear state space model. So you develop a dynamic model in this form, develop the control objective, define the control objective, and develop the output map equation, and then rearrange the equation 1 and 2 so that you can get a control affine nonlinear state space form. For the linear state space model, what you have to do is you have to linearize this equation 1 and equation 2. You have to linearize the equation 1 and equations 2 around some nominal value of x's and us, around some nominal values of x's and us, and form the linear state space equations after subtracting steady state equation from the nonlinear equations or unsteady state equation, after subtracting the steady state equation from the unsteady state equation. And if you do that, then we'll have this linear state space model. Okay, so this is basically the methodology for developing a state space model, whether it's a nonlinear state space model or a linear state space model. So let us just go into details on the development of this linear and nonlinear state space model, specifically the linear state space model. So in case of a linear state space model, we develop the dynamic model in a form x dot is equal to fxu, y is equal to hxu. Here again, x is of dimension of n, u is dimension of m, and y is dimension of p. So now we use the Taylor series approximation around this x and us vector and neglecting the higher order terms. So we'll get x1 dot x is basically a vector of x1, x2 to xn. It's a dimension of n. So if I take only for the x1, then it will be, because for the x1 it will be x1 dot is equal to fxu. So here also I will got x1 dot is equal to the steady state component. F1 x1 is steady state function plus the Jacobians. Del f by del x1, x1 minus x1s, del f1 by del x2, x2 minus x2s. So del f1 by del xn, xn minus xns. Similarly, for the u also, I will write plus del f1 by del u1, u1 minus u1s, del f1 by del u2, u minus u2s. It will continue up to del f1 by del um minus ums. Okay. This sort of equations I will go on writing for the x1 dot, x2 dot to xn dot. So for the similarly, in a similar fashion, I will write the equation for the xn dot. So for the xn dot also I will write this equation. Here only the f1 will be replaced by the fn. All other terms will more or less remaining same, and I will get the xn dot equations. Now all these equations, if you arrange all these equations, if you arrange, and then you subtract the steady state equations. You subtract the steady state equation. Steady state equation is x1 dot s equals to this term only. Steady state equation is x1 dot s is equal to this term. So I subtract from this equation the steady state equation. So this term will vanish. So I will have in the deviation form only these terms. Okay. So then we can write x1 dot x2 dot xn dot in a form like this. Del f1 by del x1 by del f1 by del xn, del fn by del x1 by del fn by xn. So I will have a matrix n by n matrix into x1 x1 to xn vector. Similarly, I will have a n by m matrix, which is associated with the input vectors u1 or control vector u1, u2, and un. Okay. So I will have this equation x dot, this is x dot, ax plus bu. This term is basically called the A, and this term I can call is this matrix I can call it B. So A is defined as the Jacobians of the functions with respect to the state variables. A is basically defined as the Jacobian of the function or derivative of the functions with respect to the state variables. So Aij, each element of A will be Aij, small aij will be del phi by del xj. And B is the derivative of functions with respect to U or the input variables or the control variables. So B elements of each element of B matrix will be B, small bij will be del fi by del uj. Okay, so these basically the state equations I have developed. In a similar fashion, the output map or the output equations, which is y is equal to h, x, h is a function. So I write for y1 in a similar fashion in terms of x state variables since age and then in terms of the input variables. In a similar fashion for all the y's, if I write from y1 to yp, if I write the equations, I will end up to this series of equations, p number of equations which have got these derivative terms which linearizes these nonlinear equations. Now I subtract from the steady state value. These are the steady state component. So y1. So this steady state component, if I subtract, this will vanish, and I will have only the dynamic component, which if I rearrange, then I will have equations like this: y1 to yp, then the derivative of h with respect to state variables multiplied by the state vectors, derivative of h with respect to the input vectors multiplied by the input vector. So this is basically y is equal to cx plus du, where c is basically the matrix containing the derivative of h with state vectors, and the d is the matrix containing the derivative of h with respect to u vectors. So the c and d are accordingly defined. Okay, so in this fashion we can develop the state space model, linear state space model from the dynamic model. Okay. Now once we have the linear state space model, then that linear state space model I can convert to the transfer function model. So I have the linear state space model x dot is equal to ax plus bu, y is equal to cx plus du. Then we take a Laplace transform on that. So if I take a Laplace transform, Sxs is equal to ax plus bus, x0 will be equals to 0 because since this is in terms of deviation variables. So and ys will be given by cxs plus dus. So if I do algebraic manipulations on this, then we'll have si minus axs. I put this term over here, si minus axs. I have to use identity matrix over here because these are all in vector matrix form. So si minus axs is equal to bus, which means xs will be si minus a inverse into b into us. Then ys will be c into si minus a inverse b plus d into us, because I know xs is equal to this term, so I put xs over here and I will get ys is this term. So here I will get ys is equal to gs into us. So in a general form, I will get a Laplace transform model ys is equal to gs into us. But in actual practice, this u contains both the input vectors, which contains the manipulated variables as well as the distance variables or the noise load variables. So normally a transfer function model is expressed in terms of process and the disturbance transfer function. So the input variable u are now partitioned to manipulated variable m and load disturbance variable l. So the u I can write as m and l, so that I can write ys is equal to c si minus a inverse bm plus dm into ms plus c si minus a inverse bl plus dl into l. Okay, so this is basically your process transfer function GPS. This is the process transfer function GPS, which is related with the manipulated variables, and this is the load transfer function or GLS, which is related to the load variables. So this is basically the methodology from the converting from the linear state space model to transfer function model. Okay. I hope this is not so difficult. I hope this is clear to you. I'll take one example. So we'll take one example of the Van der Waals reactor. So for Van der Waals reactor, we know already the dynamic model for this. So these are basically the dynamic model dCA by dt, and dCA by dt is equal to F by V CAF. CAF is the feed concentration of A, Ca K1 Ca K3 Ca square, which is basically I can write as a function F1 of Ca Cv and F by V. Here is a function of F2 Ca Cv and F by V. Here Ca and Ca Cv is the state variables and F by V is the input variables. Here also I am taking F by V, ratio of F by V, which is basically the space velocity, is the input variables. Okay, so once we have this dynamic model, this dynamic model I can now rearrange to write a control affine state space model, nonlinear state space model. So in a control affine nonlinear state space model, your model is x dot is equal to fx plus gx into u. So you have to first separate out the u component. So if you separate out the u component here, u is f by v. So the f by v CAF and f by v CB has to be separated out from this equation. So the nonlinear state space model, basically here I say x1 is equal to Ca, x2 is equal to Cb, and input u is equal to f by v. And since my control objective is to maximize the production of v, so my output y will be Cb. Okay, so once we define this, then my state equations I can write, nonlinear state equation I can write dx1 by dt. So here basically I am separating out the u component over here. So with U, this is related. X1f minus x1 is related. So I write this. I separate out this one x1f minus x1 into U, and minus k1 x1 minus k3 x1 square. Similarly, for dx2 by dt, I have got a k1 x1 minus k2 x2 plus minus x2 into U. So in vector matrix form, I can write x dot, which is x1 dot, x2 dot is equal to this term is fx. This term is fx minus k1 x1, k3 x1 square, and k1 x1 minus k2 x2. This function vector is the fx plus this is the gx. x1f minus x1 minus x2 is the gx multiplied by u, the input vector. So this is basically the nonlinear state space model, which is pretty simple. Once we have the dynamic model equation, then we can easily write this control affine form of this form. Okay. Here, one thing you have to keep in your minds, in this equation, it is pretty easy to separate out the component of u. That means it's pretty easy to write down these equations as fx plus gx into u. There are many cases where it is not easy to separate out the u component. That means it's not possible to write this equation in a control affine form. Then these nonlinear state equations will be x dot is equal to fxu. And the output map, here we have seen output y is equal to cb. So if it's y is equal to cb means y is equal to hx, which will be the 0, 1 into x1, x2. So it is y is equal to x2. So y is equal to x2 means in vector matrix form, y is equal to 0, 1, x1, x2. Okay. So in this fashion, we can write the nonlinear state space equations. Now for the linear state space model, for the linear state space model, we have to use these dynamic model equations. This f1, so dCA by dt and dCB by dt is equal to f1 CSCB f by v and f2 CSCB f by v. So we'll linearize the f1 CSCB f by v, and if we and f2 CSCB f by v, these two terms if we linearize as considering x1, capital X1 is CA minus CAS, capital X2 is CB minus CBS, and U, capital U is f by v minus f by v at steady state or nominal value. So in that case, we know already A will be given by, for the x, this is x dot is equal to ax plus bu. So the A is basically the derivative of the functions in terms of the state variables. So state variables are CA and CB. So A will be del F1 by del CA and del F2 by del F1 by del CA, del F1 by del CB, del F2 by del CA, del F2 by del CB. So if I find out the derivatives from these equations, if I find out the derivative from the equation del F1 by del CA, I can easily find out from here, and I will get this term over here, this term, this term. So I will get the A component. Similarly, I can get the B component. Similarly, I can get the B component. So as I have these functions f1 and f2, and easily I will get the B component by putting the derivatives of the f1 and f2 in terms of the state variables and in terms of the input variables. And the C will be same. Basically, it's a C component is a linear equation, so it will remain same. C will be 0, 1, and D will be equals to 0. So I will have x dot is equal to ax plus bu and y is equal to cx plus d. Okay. So this is basically the way we can develop the linear state space model. And from this linear state space model, I can convert to a transform domain model writing this equation Ys is equal to CSI minus A inverse B plus D US. Since D is equal to 0, so this will be C into Si minus A inverse B US. And I know Si minus A. So Si minus A I will write, which will be S minus A11 minus A21 minus A12 S minus A22. Okay. So I will write the Si minus A inverse. So these two exchange places, and this will become, this will be, place will be exchanged over here, their sign will be changed, place will remain same. So by 1 by determinant of this matrix. So this will be Si minus A inverse, and then where determinant will be given by this term, and then I will get Si minus A inverse. C is 0, 1 into this term. So since it will be 0, 1, so only one component will be there. So I will have this component will become 0. So this component I will have, so 1 by determinant A21 S minus A1. So CSI minus inverse B will be this component, which will be basically these equations. So I will get a transfer function form of Ys by Us of in this form. Okay. So this is basically the transform domain form, and if I put the component of A11, A21, and so on, so finally I will have the transform domain equations, transform domain or transform domain model for the Y of this Van de Bossche reactor in this form. Okay. Here basically you can see this is a equation of you have got a 1, 0 over here, you have got a 1, 0 over here, and that 2 poles over here. These are basically 1, 0 and 2 poles over here. And depending on these values, this 0 either may lie on the right hand plane or the left hand plane or on the imaginary axis itself. Okay. So this is basically the methodology for converting or developing a state space model and the transform domain model from the basic dynamic equations. Now, in actual practice, we have got, let's say, for a process, if we have already developed a transfer function model, from a practical data or experimental data. So we have an existing process. On that existing process, we have done some experiment. We identified input and output. We have done some experiment, and we have developed a transfer function model. Now, if we have a transfer function model, can you realize the state space model from the transfer function model? So the next section is the state space realization from transfer function model. Okay. So in this case, let's say we have a transfer function model available with us already. So can we build a state space model from that transfer function model? Now this process of converting the transfer function to state space form is not unique. There are many ways of doing it. And the many form of state space model we can get, which means that various realizations are possible. However, the fortunate part is that all these realizations, you can have various realizations, but all these realizations are equivalent. Otherwise, it would have been difficult to convert the transfer functions to state space and convert all the knowledge of the control theory of the transfer function model based on the transfer function model to the state space model. only thing, since there are various realizations possible, it may so happen that one type of realization have some advantages over other types of realizations for a particular task. So this why this statement is you will not understand right now, but later on as you go on developing the controller for the state space using state space model, then it will be clear to you why some realizations have advantages over other realizations. Now, what are the possible realizations? The possible realizations are the first companion form, which is called the controllable canonical form. The second is the Jordan canonical form. And the third one is the alternate first companion form to Eblis form. And fourth is the second companion form or observable canonical form. So normally these four types of realizations are possible. I will not say possible, there are possibilities many, but these are the four types of realizations are normally used. So let us start with the first companion form or the controllable canonical form. So in a controllable canonical form, we'll take a generalized transfer function model. And this transfer function model is the rational transfer function model. If you have a non-rational transfer function model, like first order with date time system, then the date time component or the non-rational form has to be converted to a rational form. Like for a date time system, you can convert the date time system to a rational form using per day approximation. So you can use a per day 0th order approximation or first order approximation or per day 2x2 approximation and so on. Okay. So I will have a rational transfer function of general form is B0 Sn B1 to the power n minus 1 by Sn A1 Sn minus 1 An minus 1 An. Okay. Here basically I have taken both the orders as same, but if it is a perfect rational transfer function, then it will be this numerator order will be less than the denominator order. So now this ys by us I can write as ys by zs into zs by us. That means I am separating out the numerator and denominator part. So the denominator part I write this one into the numerator. The denominator part I write this way 1 by this thing, and the numerator part is b0 b1 bn minus 1s plus bn. So here basically I say zs by us is this part 1 by this term. So if it is so, and ys by zs is this term. Okay. Now zs by us is this term, then I can write in a differential equation form is basically a nth order differential equation form. d z by dn z by dtn a1 dn minus 1 z by dtn minus 1 and so on equals to u. Now I define states x1 to xn as x1 is z, x1 equals to z, x2 is equal to dz by dt, x3 is equal to d2z by dt square, and xn is equal to dn minus 1 z by dtn minus 1. So now I define the states x1, x2, x3, and xn in terms of z. So x1 is z, and the first derivative of z is x2, second derivative of z is x3, and n minus 1 derivative of z is xn. So if it is so, then I can write x1 dot. x1 dot is dz by dt is equal to x2. So x1 dot is equal to x2. Similarly, x2 dot is equal to x3, and xn minus 1 dot is equal to xn. This is xn minus 1 dot. So xn minus 1 dot is equal to xn. And xn dot, that is that this term xn dot is basically this term over here. So dnz by dtn is basically xn dot. This equals to u minus this term, u minus a1 n minus 1 derivative of z that will continue to derivative, first derivative of z and then the zeroth derivative of z. So u minus this term. So here also I write xn dot is equal to minus an x1 minus an minus 1 x2 minus a2 xn minus 1 minus a1 xn plus u. So when I'm writing the xn dot, I utilize these equations. I utilize these equations to write down the xn dot, the final state equations. So now I have the state equations of x1, x2 to xn dot in terms of state variables and the input. Now for the output map, we have ys by zs is equal to these equations that we have already separated out. So ys by zs is this one. So ys will be in terms of differential equation, yt will be b0 dn nth derivative of z plus b1 into n minus 1th derivative of z. That will continue till bn minus 1 first derivative of z and then bn z. Now the dnz is basically xn dot. This one is xn. This one is xn minus 1. So this will continue. Then I will get bn x1. So I will replace the z in terms of x1, x2, xn. Now this xn dot, I know the expressions already from the state equations. So from the state equation, xn dot equations is known to me. So I put this xn dot equations over here. I put the xn dot equations over here. Then I will have separate out the coefficients of x1, x2, x1 and u. So I will separate out the coefficients. I will get bn minus an b0 x1, bn minus 1 an minus 1 b0 x2, and this way will continue up to plus b0 u. So the y output map I will get in this form. Okay. So in a standard vector matrix form, then I can write x1 to xn. So x1 dot is equal to x2. So I will have 0, 1, but other terms are 0. Similarly, I will have x2 dot is equal to x3. So that I will have this element, other elements will be 0. So this way I will have this equation into u. Similarly, for y output map will be this one into multiplied by the state vector plus b0 into u. Okay, so this is basically a controllable canonical form. In the controllable canonical form, you can see basically the representation is pretty simple over here. So here the structure you can see over here. And these components are the coefficients of in the transfer function. These are basically the coefficients in the denominator transfer function. And these basically, these elements contains the coefficients of both the numerator and denominator polynomial of the transfer functions. So this is basically called the controllable canonical form. Next, I will have a Jordan canonical form. In a Jordan canonical form, we take these transfer functions, the general transfer function, in terms of a partial fraction form. So we apply partial fraction and we write this in a form like this. So we'll have b0 plus r1 by s minus lambda 1 plus r2 by s minus lambda 2 plus rn by s minus lambda n. Okay. So once we write this general form of transfer function in a partial fraction form, then we write gs is ys by us. So we write ys is equal to b0 us into r1 us, r2 us, and so on. Which I write in a sense that b0 us plus r1 x1 s. So I write us by s minus lambda 1 is equal to x1 s plus r2 x2 s plus that will continue till rn xn. So us by s minus lambda 1 x1s, u by s minus lambda 2 x2s. Similarly, u by s minus lambda n is xns, where x1, x2, xn are considered as the states of the system. Now, once I define these as x1, x2, and xn, then writing the state equation is pretty simple. So that means x1 s is equal to us by s minus lambda 1. So in the state form, it will be x1 dot is equal to lambda 1 x1 plus u. Similarly, here x2 dot will be equals to lambda 2 x2 plus u. So this will continue till xn dot equals to lambda n xn plus u. So I will have the state space state equation in the vector matrix form is x1 dot x2 dot x3 dot xn dot into ax plus bu. Here in the A you see only the elements, diagonal elements are finite, other are there are non-zero elements, and other elements are the zero elements, and the other elements are zero. So the diagonal elements are only the non-zero elements, which are basically the roots of that denominator polynomial. Okay, and the output map we can write y is equal to r1 x1 r2 x2 plus rn xn plus b0 u. This basically we have written already. Ys is equal to this term. So if I take inverse of Laplace, this will be yt is equal to b0 u plus r1 x1 plus r2 x2 to r1 rn xn. So I will write y is equal to r1 x1 plus r2 x2 rn xn plus b. Okay. So this is basically the Jordan canonical form. So controllable in the controllable canonical form and the Jordan canonical form, you can see they are two completely two different forms. In the Jordan canonical form, basically now all the states are, I will say, delineated, or their interactions are minimized. So these are now states are basically non-interacting in nature. All the states equation, this is basically dependent on x1, this one is dependent on x2, this one is dependent on xn only. So this way, basically, I have broken the systems to individual n number of individual systems. What will happen in the case of repeated roots? So if in the transfer function, if you say in this transfer function, if I have a s minus lambda 1 to the power q, s minus lambda 1 to the power m, and then s minus lambda 2 and s minus lambda n minus m, and so on, then what will happen, right? Okay, so I think it's already nearly 11 o'clock. So this part I'll discuss in the next class. Okay, so if you have any questions, you may please ask. Do you have any questions on this? Hello? Okay, then. So I think in one of the class I have to take a quiz on this, since it seems everybody, either you have everything you have understood or you have not understood anything and do not want to ask the questions. Anyway, so if you do not have any questions, I am ending the meeting over here. Thank you very much.
Thank you, sir.
Thank you, sir.